and welcome back. We were discussing in the last class about states of matter, which is unit 5 of the NCERT class 11 textbook in chemistry. Let us quickly recap what we did yesterday. We started off by saying about different states of matter, where we believe that we would be able to identify different chemical substances and their states of matter. We also started discussing about intermolecular forces. In which we discussed ion-ion interaction. And the reason for having intermolecular forces, discussing intermolecular forces, is of course that it is the factor in combination with the temperature which determines the state in which a substance exists. And with regard to ion-ion interaction, with sodium chloride as the example, we said that the potential energy varies as 1 over r. We started our discussion yesterday about ion dipole forces. So, let us go back and continue that. If you take sodium chloride solid and dissolve it in water, then sodium chloride will dissociate and give you Na plus ions and Cl minus ions. And each of these ions, sodium and chloride ions, will be surrounded by water molecules. There are a number of layers of water molecules around it. We have just drawn the first layer around the sodium ions, and similarly for the chloride ion. And there is an interaction which leads to this kind of behavior in these systems, and that is the one that we are trying to understand now. So, we already know that there is an electronegativity difference between oxygen and hydrogen, with oxygen being more electronegative than hydrogen. So, if you take one particular bond of the water, which is the OH bond, we expect that although we expect that the electron density will be symmetric, if the two atoms were the same, because oxygen and hydrogen have an electronegativity difference, in reality you will see more electron density around the oxygen and less around the hydrogen. So, there is a delta minus charge, a partial electron distribution with partial electronic charge higher on the oxygen side and lower on the hydrogen side. So, you have a delta minus delta plus situation in each of these OH bonds in water. So, this is what we call a dipole, and it is represented in this fashion, where this is the positive side and this arrowhead is the negative side of the dipole. So, in water I have one dipole oriented like this and another dipole oriented like this. And when a sodium plus ion comes, you are going to have an interaction between this positively charged ion and this dipole. So, I would have a situation where I have a positive charge and a dipole like this. There is also the other possibility, because the water molecules and everything else in the liquid state is undergoing motion, I would also have at some point a situation where this happens. This is energetically more favorable, whereas this is energetically less favorable. But because molecules are in motion, sodium ions move when in water, the water molecules also tumble. So, you are going to have situations where all of this exists in the solution. And there is an interaction between the ion and the dipole, and similarly I would have the situation where I have Cl minus would also interact with the dipole. In this case, the favorable interaction would be the other way around, which is why when I drew this picture, I drew it with the hydrogen side closer to Cl minus and the oxygen side closer to Na plus. So, I have this interaction of Cl minus or any ion with the dipole, and this is what we would like to see. And this interaction, the potential energy of interaction between the ion and the dipole is proportional to 1 over r square. You compare this with the electrostatic case, V electrostatic or ion, and this was proportional to 1 over r. So, we will not worry about what the constant is. So, imagine that the constants were the same. So, the ion dipole interaction will go as k over r square, whereas the ion interaction goes as k over r. So, if you plotted potential energy, and I am looking at this as an attractive potential, we already know that 1 over r goes like this, and so this is the potential energy in joules, imagine, and this is r, and I do this in scaled coordinates. So, I divide it by something, so that r 0, so that this gives me a unitless quantity. So, rather than having a dimensional r, I am looking at it in terms of a unit which is dimensionless. So, I have divided it by this, and at this point this is 1. Now, on the same graph, I would like to look at how 1 over r square looks. So, if you plotted 1 over r square on this, at r over r 0 equal to 1, both these things will intersect, whereas for larger distances of r over r 0, this term is going to be smaller. So, it looks something like that. So, this is the 1 over r square or k over r square term, the thing in red, and the one in black is k over r term. And what you will notice is that as you go to long range, that is for large values of r over r 0, the 1 over r square term, that is the red one, is small or is smaller than the 1 over r term, whereas at short distances, that is here, the 1 over r square term is bigger than the 1 over r term. And in general, you will find when you have potentials which look like 1 over r to the n, larger the n, and I am looking at attractive, larger the n value, shorter is the range of the force. In other words, the electrostatic 1 over r acts at long distances and 1 over r to the n, where n is 2 or greater, acts at short distances. So, this is sometimes called the short range forces. And it turns out that e to the minus k r would be the shortest range, but that is not something that we will have to worry about. So, this is a difference in how the 1 over r square term behaves differently from the 1 over r term. And any time you have something like sodium chloride or lithium fluoride and you put it into water, this dissociates into ions, and if the solvent has a dipole, you are going to have ion dipole forces which come into play. So, if you wish to look at an example of where this effect is seen, you consider the hydration enthalpy of a series of ions. So, here is the ion, here is the ionic radius of the ion in picometers, and there is the delta H naught of hydration, which is given in kilojoules per mole. So, for Li plus, which has an ionic radius of 76 picometers, the hydration enthalpy is minus 538 kilojoules per mole. Na plus, what do you expect the ionic radius to be relative to Li plus? We know from the periodic trends, if you went down the period, when you go from Li plus to Na plus, the ionic radius would increase. And if the ionic radius increases, we expect that the hydration enthalpy would decrease. And sure enough, the hydration enthalpy, which measures if I have an ion Mn plus in the gas phase plus H2O giving Mn plus aqueous. This is the delta H that we are measuring here. So, smaller the ion, larger is this thing, and this trend continues. If I went to K plus, whose ionic radii is bigger than that of even Na plus, the enthalpy of hydration is even smaller. Now, this is for the alkali metal ions. If you went to the alkaline earths, Mg2 plus has an ionic radii similar to Li plus, but because of this doubly charged nature of Mg2 plus, its hydration enthalpy is significantly higher than that of Li plus, although its sizes are almost the same. And if you went to Al3 plus, it has an ionic radii much smaller and a hydration enthalpy which is much bigger. So, this illustrates the trend that you see as you go down the period. For the same charge, as the ionic radii increases, the hydration enthalpy decreases. Understandable. I am taking a singly positive charge, I am distributing it over a sphere. So, the larger the sphere, the lesser is its interaction, because on the surface there is less charge. So, that is all that is happening. As the radius increases, the hydration enthalpy decreases. And the same thing happens here with Mg2 plus, you have larger charge distributed over the same radius, so interaction increases. So, this is how you would. So, now given this, you should be able to predict under what situations, so relative sizes, and also under what situations this force we expect to see. So, here is something that you can do as a self check. In which of the mixtures, in which mixture do you expect higher ion dipole forces between solute and solvent? And the choice is between methanol in water and calcium nitrate in water. So, you will have to approach it, you have to see which of these two things, two solutes, when you put it in water will ionize. So, you need to know the character of the solute from your previous knowledge of chemistry, and the one which will have smaller size or higher charge is going to have a higher interaction with water. And so, in that situation, that is the compound in which, that is the mixture in which the ion dipole forces will be higher. So, that is how you approach this problem. So, thus far we have come across two things. We have looked at ion-ion and ion dipole. And you remember, let us just recap from last class: ion-ion, ion dipole, dipole-dipole, and a part like dipole-dipole is the hydrogen bond, which would come somewhere, we will not worry about this yet. Dipole-induced dipole, and induced dipole-induced dipole. That is what we have. So, we have done this thus far, and in terms of sizes, hydrogen bond will be here. It is special in some sense, so I will circle it in red. It is a type of a dipole-dipole interaction, but it is stronger than a typical dipole-dipole. We will come to that after we have discussed the dipole-dipole. Okay? So, we have done this and we have discussed this. So, you should now be in a position to identify these two forces, where it exists, then their strengths based on what we discussed in terms of their R dependence and the sizes and the charge, etc. So, the next thing that we will consider is the dipole-dipole interaction. You take nitrogen, which is a gas at room temperature, but can be liquefied. It has a molecular mass of 28 and a boiling point of 77 Kelvin. Oxygen gas can also be liquefied, has a molecular mass close to 32 and has a boiling point of 90 K. NO has a molecular weight of 30, and if you think like I do, I would imagine, so there is one atom for now of nitrogen, one atom of oxygen in NO, and I would imagine that the boiling point of NO would be somewhere between 77 K and 90 K. If you thought intuitively, that is what you expect, because you have taken one atom of nitrogen, one atom of oxygen, put it together to give nitric oxide, which is a gas. We expect that its boiling point would be somewhere in between. But interestingly, the boiling point of NO is 121 Kelvin, which is significantly higher than either this or this. And if you thought about it, The reason for this is dipole-dipole interaction. So, nitrogen, so what is the difference between nitrogen, oxygen and NO? Nitrogen and oxygen are symmetric. Both of them, which means that it does not have a dipole moment at equilibrium, whereas NO has a dipole moment arising because of the electronegativity difference between nitrogen and oxygen. So, there is a dipole moment, and this dipole moment is what leads to the higher boiling point. So, what is it that this dipole in NO which causes this to happen? So, presumably there is an interaction between a dipole like this and another dipole like this. So, if you draw it in terms of the electron density, I would have some situation like this, delta minus, delta plus would interact with another molecule which is delta plus, delta minus, and there is an interaction here. And this interaction we know from electrostatics, which you must have studied or will soon study. This interaction energy, if the two dipoles were static, is given by mu 1 mu 2 over some k r cube, where mu is the dipole, which is E times r. So, that is the dipole, and we are saying this is mu 1, this is mu 2, and if r is the distance between the two dipoles, this is how, if the two dipoles were static, this is the interaction energy. But in liquids or in gases, these dipoles do not stay like this, right. So, I would have a situation where this is the lower energy because the negative end of one dipole is closer to the positive end of the other dipole, and so this interaction energy is going to be higher than, or is attractive, more attractive than if you had this situation with the two dipoles oriented like this. And when the molecule tumbles, you are going to have this situation, and you also are going to have this situation. But energetically this is more favorable because I have the two dipoles oriented like this. So, this will attract this. So, this is more favorable than this, but this also exists. So, in a liquid or in a gas, these dipoles of NO are tumbling around. So, then the interaction energy is no longer in this fashion. If it is not static, average over all possible orientations of the two dipoles, this will go as 1 over r to the 6. So, to recollect, electrostatic V ion is proportional to 1 over r, V ion dipole is proportional to 1 over r square, and V dd is proportional to 1 over r to the 6. So, you can now draw this picture once again. I plot V as a function of r over scaled distance between the two dipole or the two ions, or the interaction sizes are different, but we will consider that they are all of the same size. So, 1 over r would be like that, 1 over r square. So, imagine that this is 1 at that point, they are equal. So, it will go like that. So, this is 1 over r square, this is 1 over r, and if you plotted 1 over r to the 6 at the same point, it will lie on top of all of the others, but it goes even steeper, and this is 1 over r to the 6. So, which means that this is even more short range. So, the dipole-dipole interaction goes as 1 over r to the 6. And there are many instances where this thing happens, where you see dipole-dipole interaction. So, if you took, for example, HCl in water, then you have a dipole oriented like this. Or you take, for example, CH3Cl or CH2Cl2 and CHCl3. This is a series. So, in CH3Cl, we have a dipole oriented in this direction. The electronegativity difference between carbon and hydrogen is small enough that you can ignore that. Now, if you have CH2Cl2, then you have two dipoles oriented like this, as in the case of water. So, in this situation, for example, you have two dipoles, one oriented this way, another dipole oriented that way, and the resultant would be from the parallelogram law. So, you have mu 1 here, mu 2 here, and you will get the resultant would be in this particular direction. You could do the same thing when you have 3 of them, as would be the case if you have CHCl3. And you can do vectorial addition as you have done here, and to get the resultant dipole. So, here are, so we have come across now a dipole-dipole type interaction, which goes as 1 over r to the 6. So, we have 1 over r, 1 over r square, 1 over r 6, all of them are attractive. But we also said at the beginning in the last discussion that if you put two things and put them closer together, the electron densities will start to overlap and there will be a repulsive potential as a result of electrons clashing with each other through what is called by the Pauli exclusion principle. This is repulsive when the atoms, the atoms or molecules get closer together, and this is 1 over r to the 12. So, these are all negative in sign. So, they bring the things together, whereas this one will tend to throw things apart. So, this is positive. So, if I plotted this, r to the 12 is an example, it could be something else, it does not matter, but what it means is that it is even shorter range. So, at very short range, the repulsive forces will start to kick in. So, if I plotted this repulsive potential V as a function of r over r 0, it will go very steeply. So, this is very steep and very short range. So, in a molecule, you have this attractive potentials when the intermolecular separation is reasonably small, that is it is a little bit apart, but as you bring them too close, the repulsive part will start to kick in. So, the sum total of these things, so intermolecular forces, no matter what the type is, if you plotted V as a function of the distance between this, what we are saying is these attractive forces will act initially and the energy will start to go down. This is not very important at very long range. This comes down, and at some point when this becomes too close, this repulsive force will start to take over and the energy would rise. So, this is the repulsive part, which will look very often as 1 over r to the 12 or something bigger than that, and this is the attractive portion. So, this well depth will be determined by the size of the attractive and the size of the repulsive terms. So, this well depth and this position here, this equilibrium distance. So, there are two things that affect it. So, there is this well depth and this distance, and we already said that this well depth will affect the temperature at which a substance is a solid or liquid. If the well depth is very high, then you need to provide lot of energy, which means that you have to raise the temperature to a higher values before you can get it into the gas phase. So, moving on. So, we have discussed ion-ion interaction, ion dipole, and we have talked about dipole-dipole. And we mentioned a particular form of this, of the dipole-dipole, is the hydrogen bond. And let us take a look at some data of the boiling point. You look at the boiling point of methane, whose molecular mass in AMU is 16, and its boiling point in Celsius is minus 161.5. Silane SiH4 has a molecular mass of 32 and a boiling point of around minus 112. Stannane has a molecular mass of 122 and a boiling point of minus 51.9, where plumane has a molecular mass of 211 and a boiling point of minus 13. So, if you plotted boiling point in degree Celsius as a function of molecular mass, you find that it almost goes up linearly in this series of hydrides of the group 4. Now, for comparison, let us look at in the next period ammonia with a molecular mass of 17 minus 33.33. pH 3, if the prediction with regard to this boiling point that we learned from the methane series was right, we would expect that this would be smaller than this, has a boiling point of minus 87.75, which means that it has gone down. Arsine, the molecular mass close to 78, minus 62.5, and stevene with 125 as a value which is higher than this, but I think I have made a mistake in my notes. So, it is something here. So, I will leave this for now because, but its value is higher. So, if you plotted this boiling point as a function of mass, molar mass, this goes like this, that is NH3 is much higher than this, and it is even more dramatic when you look at water with molar mass 18 is close to 100, H2S molar mass 34 minus 60, H2SE hydrogen selenide molar mass of minus 41, and H2TE 130 with a boiling point of minus 2. Again, boiling point versus molar mass, there you go. There is something strange that both ammonia and water, and if you looked at the hydrogen halides, that is HF, HCl, HBr, HI, which look similar to this. So, there is something strange about ammonia, water, HF, which makes it different from the rest of the compounds in this series, and this is the difference arises as a result of hydrogen bond. So, what is the hydrogen bond? If you have a hydrogen attached to an electronegative atom, so hydrogen attached to an electronegative atom, so this will become delta minus H plus, then this hydrogen atom could be shared with another electronegative atom like this. So, if I have XH where X is electronegative, then you could have in principle a bond between Y where X and Y are electronegative. So, that is the case with ammonia, where the NH bond, because of the electronegativity difference between nitrogen and hydrogen, is high enough that you have this situation, and this is an example of a hydrogen bond. And this is a very strong bond relatively compared to the other intermolecular forces, and this is critical for the properties of water. So, the anomalous properties of water chemically arises because of this. So, there are many instances where we have hydrogen bonding, and so if you have hydrogen bonding, the properties of that compound are slightly different. So, let us take the case of, if you took, could you predict using this knowledge which of ethanol and dimethyl ether would have the higher boiling point? So, ethanol is C2H5OH and dimethyl ether is CH3OCH3, which means that the molecular masses, molar masses are the same. So, the question we are asking is, given that the molar masses of these two are the same, could we, with the knowledge that we have got thus far, predict which of these would have the higher boiling point? And if you looked here, if you have, in this case, you have hydrogen attached to an electronegative atom like this. So, this is a candidate for a hydrogen bond. So, in the case of ethanol, there is a possibility of a hydrogen bond happening. So, if you looked at water as is, or for this matter OH, so let us call this ROH, and then you could have another oxygen here ROH, that is the hydrogen bond. And if you have lots of molecules and they are hydrogen bonded together, then if you have to get this to boil, so you have to go from this is what it is in the liquid state. If you have to boil, you have to go to this situation where you have molecules that are free. So, you have to break this bond, and the more bonds you have to break and the more stronger this bond is, you will have to provide more energy, which means that you have to go to higher temperature to boil this. So, ethanol, you would imagine, has a higher boiling point. So, ethanol has a higher boiling point, you would predict, than dimethyl ether. So, this is the way one would analyze this particular situation. There is a very good example of a molecule which is extensively hydrogen bonded, which one uses, which is one used, and this is what is called Kevlar. This was developed by a company called DuPont in somewhere in the 1950s, and this is a very, very strong material which is used for bulletproof jackets and things like that. And its properties, very strong material, and its property that it is a very strong material is to a large extent governed by its structure. So, this molecule Kevlar is a polymer with this structure. And this repeats. So, a polymer is this repeating. Now, if I have one chain like this and if I have another chain, which comes close to this, now you can see what happens. This is hydrogen bonded here, this is hydrogen bonded, this is hydrogen bonded, this will hydrogen bond to the one on the other side, and you can now see what happens. So, you have all these chains with both the carbonyl group. So, this will then hydrogen bond with another hydrogen, because now you have an electronegative atom, a hydrogen here which is attached to a nitrogen here. So, which is electronegative. You have a series of hydrogen bonds. So, you make this sheet where each element of the sheet is this long fiber. So, it is hydrogen bonded in such a way, and it provides it a lot of strength. So, this is an example where the hydrogen bond is used to create a material whose property is very useful. In real life, you have DNA, deoxyribonucleic acid. This is also that you will study later on in both chemistry and if you are studying biology, hydrogen bonded. So, hydrogen bond in DNA is determined a lot of the things in life. So, thus far what we have done is to look at ion-ion interactions. So, before we close for today, we will just go over this, because I said one of the things that I said was that you should be able to list the forces that you have, intermolecular forces. So, you have ion-ion interaction, ion dipole interaction, dipole dipole, and this is where we also have the hydrogen bond, which is stronger than the ion dipole. So, you write it this way and you stick it in here. So, the strength of the interaction goes like this. So, I think we will close at this point for today, and tomorrow on the next class we will discuss other forms of interaction, which is dipole induced dipole, and induced dipole induced dipole. To give you a glimpse of what will happen, imagine, why does oxygen, for example, dissolve in water? The reason that oxygen dissolves in water is because of this dipole induced dipole. Oxygen itself does not have a dipole, water has a dipole, but when you dissolve water in oxygen in water, you have a dipole induced dipole interaction. We will come to that in the next class, and then we will discuss dipole induced dipole and induced dipole induced dipole in the next class. Thank you.